1, 2, 3. One, two, three. Hello, everyone. Right. So today's webinar will be led by David Vaccaro again. Yes, so, and they will be published, maybe not today, but both webinars from last week and this week will be published by the end of this week, that I can promise. Sorry, just been busy with lots of things going on, and yeah, I'm back on track on Thursday. Right, so we'll just wait for David. Physics is almost ready. It's today or tomorrow. So most likely tomorrow is a more likely day. So it won't be coming out soon. Actually, on second thought, it might be Friday, but definitely this week. So by Friday, we've published. Hello. Right. So just check everyone's here. Ah, David is here.
Hello, David. Good evening, everybody.
Hello.
How is everybody today? I'm going to turn on my video. We had some combinatorics. We had some combinatorics last week. Oh, why is my video still off? We had some combinatorics last week. We've got a sequel today, and I'm going to focus mostly on the probability questions. How does that sound? Cool. Is this the last webinar of the year, Vlad?
It's definitely the last math webinar.
Definitely the last maths one. So let's try and make it a good one. I will share my screen. Okay. So this question is adapted from one of the questions on the sheet. And I think it's a good illustration of the techniques that you might use in probability. I'm going to show you 3 different ways of doing it. And it'd be interesting to maybe have a vote at the end of which one you prefer. As ever, if you're watching this sort of on catch up, I'd really strongly recommend pausing the webinar, trying the problem yourself, and then going through it. So, can people see my screen?
Yeah, I can't. Sorry, David, I can't stay today, so I have to be somewhere. I'll leave you to it. So,
okay,
yes.
Not a problem. Not a problem at all. Okay, so it says Alvin rolls a dice, and it says if the total is odd, he wins. If it is even but not a 6, he loses. Now, what happens therefore if he rolls a 6? Well, if he rolls a 6, then he's allowed to roll again, and the game starts from the beginning. So again, he rolls. If it's odd, he wins. If it's even but not a 6, he loses. If he rolls another 6, then he just keeps on rolling. And the question is, what is the probability that Alvin wins eventually? I'm going to try and use the chat. This is obviously a probability question. What is your main frontline tool for probability questions? So if someone shows you a probability question, what method, have you studied? Yeah, so listing out a sample space. Why is the sample space for this game going to be quite different? Why is the sample space for this game going to be a little bit tricky? So for this game, if you're listing out all the possibilities of the game, it's possibly infinite, because you might get lots and lots of sixes. Another suggestion from the chat as your kind of workhorse probability technique says a tree diagram. So let's have a look at this from, let's use a tree diagram, and let's see what a tree diagram tells us. So on the first roll of the tree of the dice, there's essentially 3 different cases to consider. Okay, Alvin can roll a 1, a 3, or a 5, and that's with probability exactly 1/2. And if that happens, he wins. Actually, I might keep it as 3 6s. If he rolls a 2 or a 4, he loses. And that happens with 2 6. If he rolls a 6, then he plays a game. And now the game continues, so he can now roll either a 1, a 3, or a 5, and that happens with probability 3/6. He can roll a 2 or a 4, and that happens with probability 2/6, or he can roll a 6, and he wins again. So we've got wins, loses, and then I'm running out of space. Wins, loses, 6. And that's probability 1/2, a 1/3, a 6. And obviously this goes potentially on forever. What do I need to do now to find the total probability that Alvin is going to win the game? And I've got a suggestion in the chat: infinite sum. Excellent. Okay, and I've got an even better answer in the chat, which says sum of a geometric series, because what those people have seen is that the winning events, there's infinitely many of them, but they're going to form a geometric series. So the probability of this branch is just 3/6, which I will simplify to 1/2. The probability of this branch is 1/6 times 1/2, or 1/12. The probability of this branch, well, what's happened here is there's been 2 6s. So we multiply along the branches, so that's just a 6 times a 6, that's 136. And I can write that 136 squared as 1/6 squared. And then again, I win if there's probability 1/2. And then this branch is 1/6 cubed times 1/2. And now if I sum this infinite geometric series, I get that the probability is 1/2. That's just winning straight away. A 6 times 1/2, which is the probability of getting a 6 and then winning. A 6 squared times 1/2, which is the probability of getting 2 6s and then winning. I could have n 6s and then winning, and this is summed to infinity. If I take out the factor of 1/2, I get a geometric sequence of a half and then 1 plus a 6 plus a 6 squared, and so on. What's the formula for this infinite geometric progression? Well, if I consider the geometric progression, I can put A is equal to a half, the common ratio is equal to 1/6, and the sum to infinity is A over 1 minus R, which is 1/2 over 1 minus 1/6, which is 1/2 over 5/6, and that simplifies to 3/5. Okay, and that's an infinite geometric series. Okay, and I think that this is the method that I would expect to be the most common method that people would use. Is there a way to avoid this infinite? Is there a way to avoid this infinite tree? Oh, sorry. Did someone just say something? Oh, the question says, are there other methods? Yes, there are indeed other methods. And I'm going to look at a second method now, which avoids an infinite tree. And then we'll think about an even better method after that. And in some ways, I wonder whether that answer of 3/5 might be sort of, you might try and think if there's an easier way to see 3/5. Okay, but let's have a look at the second method. So this is method 2. I'm going to call P the probability of winning. And this is actually pretty snazzy. So I'm going to draw my first branch of the tree again. So there's a probability of half of winning. There's a probability of a third of just losing. And then there's a probability of 1/6 of rolling a 6. Can anybody maybe in the chat tell me, can you describe the situation that has occurred after rolling an initial 6? So Alvin plays the game. He rolls a 6. What position is he in? Excellent. So what Josh has said is the probability of winning becomes 1/6 times P. And let me just unpick what Josh has thought. So if the first roll is a 6, the game just begins again. Alvin is just in exactly the same position as he was before he even started playing. So what that means is that the probability from winning from having rolled an initial 6 is just P. And then it's 1 minus P of losing. And notice the difference here is this is not just winning on the next roll. So this isn't just one roll. This branch here is the rest of the game. Oh, that's just my wife and daughter come home from work. So they just said hello. I'm just going to shout hello back. Hello. Right. So now we can get the overall probability of winning. Which is P is equal to a half. And that's just the probability of winning on the first throw. plus 1/6, and then it's as if the game has begun again, times P times the probability of winning from that point after the game has won again. So this is the probability of winning after initial 6. Okay, and what we can see is we now get 5/6 P is equal to 1/2, and so again P is equal to 3/5. Okay, this method of noticing that the game begins again is worth giving a name, and it turns out to be quite useful in these you know, in games, is called a regeneration. So the game at this point has just started, again. Perhaps in the chat, can anybody else give maybe a slightly more intuitive explanation of why P is equal to 3/5? Now, I wouldn't necessarily recommend writing this last one in a pat paper, because it's probably easier just to write up one of the other methods. But can anyone see why 3/5 is the right answer? So method 1, method 2, method 3 go from completely computational, method 1, so probability tree diagram, summing an infinite series. Method 2 is a little bit more intuition. We look for this regeneration point. We draw a simpler, we get a saving because we've got a simpler tree diagram. This last one, the last thing is to try and really sharpen that intuition. Okay, I'm going to go to Josh's idea, which was the drawing the sample space. So I'm going to draw the sample space for the first roll. Okay. So we've got 1, 2, 3, 4, 5, and then 6. Now, when does Alvin win? He wins with a 1, a 3, or a 5. Okay, so out of these 5 positions here, okay, he wins in 3 out of 5 of them. And again, this is slightly more intuitive than computational. What happens if he rolls a 6? Well, if he rolls a 6, on the second roll, there's now 1, 2, 3, 4. There's now 1, 2, 3, 4, 5, 6. Yeah, there's now 6 possibilities of the second roll. So I've split that last box into 6 places. And again, he wins in 3 out of the 6. And then the last one splits again, and then he wins in 3 out of the 5. Overall, what fraction of this shape is shaded? Well, in each of the sort of 5 rolls that are counted, he wins in 3 out of 5 of them. If it's a 6, we just discount that box, but that box splits into a section where we win in 3 out of 5 of the normal rolls, and then the last section splits and we win in 3 out of 5 of the normal rolls. So overall, the probability of winning is 3/5. You might have seen similar sort of pictures when you sum a geometric progression. So this picture, if I split a cube into quarters and shade 1 out of the 3, and then split the top corner into quarters and shade 1 out of the 3 quarters, and then shade the middle, the top quarter again, split it into quarters and shade 1 out of the 3. What you can see is that the total that's shaded is 1/3. Now you can think of that as being the sum of an infinite geometric progression, so a quarter plus a quarter squared plus a quarter cubed and so forth. Or you can think of it as just being on each level, on each of these levels, I'm shading 1/3 of the total amount. Okay, as I say, this is probably not for your pat paper because it's almost more difficult to explain than to, it's almost more difficult to explain, but it's a nice justification of why we get 3/5. So my vote for the favorite method would probably be this method 2, where we do this trick of just using the probability P from that regeneration point. Okay, but there's also nothing wrong with having in our back pocket the infinite tree and summing the infinite geometric progression. Okay, so I'm just going to pull up the video there. Does anyone have any questions about that question? Or if people are happy, put a thumbs up and we'll move on to the next one. Super. Happy days, happy days, happy days. Okay, next question. Alice and Bob play a game. They take it in turns to roll a pair of dice. The winner is the first one to roll a double 6. And it says Alice goes first. What's the probability that Alice wins? Does anyone in the chat want to suggest a method to tackle this problem? Infinite sum. Okay, so I'm going to do Josh's suggestion, which is an infinite sum. So Alice goes first, and she either wins with probability 1/36, so she gets a double 6, and she wins. She could not win, which happens with probability 35/36. And then 2 things can happen. Bob can throw a double 6, and then Alice loses. Or Bob can not throw a double 6. So Bob doesn't get a double 6, and now Alice gets a second attempt to throw, and if she gets a double 6, she wins. Okay, and then the next time she can win is if Bob, this is where we're going to get an infinite tree, but if Bob again fails to win, because if Bob gets a double 6, Alice loses. Okay, so it's worth just my tree diagram. This first roll is Alice's roll. This second roll is Bob. This roll was Alice. This roll was Bob. And then the next chance that Alice can win is if she gets a double 6 here. So what's the infinite geometric series for Alice winning? So she could win straight away, which happens with probability 1/36. The next time she could win is here, and this happens after 2 lots of missing a double 6. And then the next time she could win here is after 4 lots of missing a double 6. Okay, and I think it was Josh in the chat who said it. We now have a infinite series. Okay, and the first term is 1/36. The common ratio is 35/36 squared. So the value of the probability is the first term, which is 1/36, over 1 minus r, which is 1 minus 35 squared over 36 squared. And it's far too late. It's far too late in the day to evaluate that without a calculator. Okay, so I'm just going to cut the next question. Not cut it, get rid of it, just move it out of the way. Can anyone think of, oh, well done, someone's found 36/71. I will find that, but can anybody think of a simpler tree to draw than this infinite tree? So I'll still draw the first toss. So we've got the first toss is 1/36, and then Alice wins. We've then got 35/36, and then we don't, so that's not a double 6. Can anyone describe in the chat what has happened at this point? There's 2 things that's, yes, so there's 2 things that have happened. So it's like the regeneration tree, in that the game has begun again, but this one is slightly more complicated. Okay, why is this one slightly more complicated? So the game has begun again, but what is different after Alice fails to roll a double 6? Excellent. So Thomas has said that if Alice fails to roll a double 6, then the game begins again as if Bob was starting. So let P be the probability that Alice wins. So 1 minus P is the probability that Bob wins. Now, if Alice misses with her first throw, okay, then Alice has become Bob. So the probability that Alice wins is now 1 minus P. And the probability that Bob wins is P. And the explanation there is that Bob has sort of become Alice. because from this point, okay, I'll call this node, node star. From that node, node star, Bob is starting. Okay, so now we can do this rate regeneration idea. We can say that overall the probability that Alice wins, that's P, are the relevant branches on the tree. So one way Alice can win is 1 out of 36. Another way that Alice can win is 35 over 36. So the probability of not winning with a double six, but then winning as if she's Bob. Okay, and now we get P equals 1 over 36 plus 35 over 36 minus 35 over 36P. And then we get 71 over 36P is 35 over 36. So P is 35 over 71. Okay. So what we have there is a is another example of finding a sort of simpler tree. Okay, riff on similar idea. So this one says, Abigail and Barry play a game. And it says a coin is tossed repeatedly. If the sequence HH appears before TT, then Abigail wins. If TT appears before HH, then Barry wins. And it says the first toss is an H. What is the probability that Abigail wins? Okay, so do people understand the game? So we could toss a coin, so it could go heads, tails, heads. But the moment we get the moment we get a run of two coins in which are the same, the game stops and we decide who wins. So here we had heads, heads. So so Abigail wins. And it tells me that the game has started with a heads. So what can happen? On the first toss, we toss, it could be a head, in which case Abigail wins. Or it could be a tail, in which case we keep tossing. If it's a head, the game continues. If it's a tail, Barry wins. If it's a head, we keep tossing. And if we get two heads, we get Abigail wins. If it's a head and a tail, we keep tossing. If it's then a head, we keep tossing. If it's a tail, Barry wins. Okay, what methods could we use to solve this problem? So we could use regeneration. Let's do that kind of last. We could also use the infinite tree. So the infinite tree, we look at the outcomes where Abigail wins. So she wins here with probability of half. She wins again here when there have been the sequence TH. So she wins here with probability of half times a quarter. She next wins here Wait a minute, I think no, she doesn't win at this point. She wins at the next point. Okay, she wins the next time here when we've had 2 lots of TH, and then the game goes back to her. So we get a half times a quarter squared. So the infinite sum would be a half plus a half times a quarter plus a half times a quarter squared. Okay, so we get infinite geometric series with first term a half, common ratio a quarter. So the sum to infinity is a half over 1 minus a quarter, which is a half over 3/4, which is 2/3. Okay, that's the infinite tree. Can anyone suggest in the chat how you could make regeneration work in this example? So again, we've got the first toss. And Abigail can win straight away. At what points could you consider there's two separate points where you could consider the game having regenerated. Okay, I'll do the most obvious one first. So we could say we toss the first coin as either a head or a tail. If it's a second tail, then Barry wins. If it's a head, then you could say that the game has begun again here. Because the earlier string HT doesn't matter, you know, that's just never going to be involved. This is at this point, it's exactly as if the game had started with a head. So at this point, you could say that the probability that Abigail wins from here is the same as the probability that she wins at the beginning of the game. So now, once you sum up, now when you sum up all the outcomes, you've got a half plus a half times a half, which is a quarter, P. So you get P is equal to a half plus a quarter P. So this is the probability of winning on the first toss. This is the probability of winning after a after a tail-head sequence. And we again get P equals 2/3. Okay, so that's considering the game regenerating here. Why could you also consider the game having regenerated after this first tail? So we've got initial toss, which is a head. If there's a second head, then Abigail wins. If there's now if the first toss is a tail, which player has the advantage after this tail? Yeah, Barry has the advantage, because notice that obviously before the game has started, you're equally likely to see heads before tails as you are to get tails before heads, assuming the coin is fair. Abigail has the advantage. So the reason this 2/3 is bigger than a half, because this first toss is ahead. But the moment you get a tail, the advantage passes to Barry. And in fact, Barry has just got the same advantage that Abigail had. So here, the probability that Barry wins is P. The probability that Abigail wins overall is 1 minus P. Okay, so we get a slightly earlier regeneration, and we can say that P is equal to a half, which is the probability of winning on the first toss, plus a half of not winning on the first toss, but then winning as if she was Barry. And we get we therefore get P equals a half plus a half, which is 1, minus a half P. So we get 3/2 P equals 1. So P is equal to 2/3. Okay, so we get the same answer all different ways. So here we've done an infinite tree. Here we've done a regeneration after 2 tosses. Here we've done a regeneration after 1 toss and a switch in sides. Okay, and it's very much a matter of taste which one you prefer. Okay, this one, the infinite tree, in many ways is conceptually the simplest. Okay, but you end up with an infinite series to sum. This regeneration after 2 steps is maybe conceptually simpler than this tricky regeneration where you swap sides. This one has got the advantage of the smallest tree. Okay. Do those examples make sense? Does anyone have any questions about that question? Just to check that people are alive and happy. Do people want to just put a thumbs up in the chat if they're happy with these kind of tree diagram game questions? Okay, got a couple of thumbs up. Okay, good. Let's move on. Just moving questions down. Okay, what I'm going to do now is look at some other probability questions, okay, which are, well, varieties. They can be done by tree diagrams, they can be done by counting methods. We need to sort of select a little bit the best way. So this question, so this is question number 12. This is from a step 1 paper. Can't remember exactly what year. So it says, I have k different keys on my key ring. When I come home at night, I try one key after another until I find the key that fits my door. What is the probability that I find the correct key in exactly n attempts in each of the following 3 cases? In part I, at each attempt, I choose a key that I have not tried before, but otherwise each choice is equally likely. II, at each attempt, I choose a key from all my keys and each of the k choices is equally likely. And then at III, at the first attempt, I choose all my keys and each of the k choices is equally likely. Thereafter, I choose from the keys that I did not try the previous time, but otherwise each choice is equally likely. Right, what I'd like you to do before doing any calculations, and I want everyone to have a go at this in the chat, is we'll call these probabilities P1, P2, P3, and I just want you to put them in order from smallest to largest. Going to wait for a few more people to try this. If you're watching this at the webinar at home, try it. Okay, so let's have a think. What is the silliest way to choose keys? So the silliest way to choose keys is the one where you're most likely to just repeat a key that couldn't be used in the lot, that you've tried before, because trying a key a second time is stupid. And if you read P2, that at each attempt I choose a key from all my keys, and each of the K choices is equally likely. So this is the silliest way of doing it. So that's P2. The best way of doing it, okay, is just to systematically work through your key ring and never try the same key twice. And that is the method which is achieved by P1. PII is P3, so III is some sort of mixed strategy. Okay, so you at least don't use the same key twice in a row. Okay, so you've at least got some memory, but your memory is shorter than P2. So the correct order of size is P2, P3, P1. Okay, that doesn't necessarily mean that that's going to be the order of difficulty of solving the question. So let's have a look at what we're asked. So it says, what is the probability that I find the correct key in, and this is important, in exactly n attempts in each of the three cases? So part I. Notice that this, on a step paper, on a GCSE paper, it would probably tell you like how many marks each part is worth. Okay, and that might be proportional to the difficulty. The step paper doesn't say that. I'm just going to let you into a secret that PI is easy, and you should be able to write down. You should be able to write down the answer pretty much straight away. So if you can, anyone suggest the can anyone suggest the answer? It's not n over. It's not n over k. It's not nk. Okay, so you're just in case I, you're just systematically working through your key ring. So you're doing key 1, then key 2, then key n in the nth turn, and then your final one will be key k. Okay, so this is, you could number your keys, and you're just doing them in a systematic order, one key after another. Now, what is the probability that the nth key that you choose is the magic key that opens the lock? Any suggestions? So someone said 1 over k to the power n. Okay, that's I'm not sure where that power is coming from, because that would be sort of opening to the power n implies you're multiplying probabilities. Here, one of these keys is going to be the right key. Okay, and it might be the first key, it might be the second key, it might be the last key, but all of those possibilities are equally likely. Okay, so the answer, so the probability that the magic key is just key n is just 1 over k. If you're writing this as on an exam, what else should you write? Let's imagine that k is equal to 10. Okay, so you've got 10 keys. What's the maximum number of times you're going to have to try if, you know, before you open the door? 10. Yeah. So you're never going to try more cases than there are keys. So for part I, the probability is 1 over k, but only if n is in the range between 1 and k. If n is bigger than k, okay, the answer is 0, because you're deterministically going to find it within k within k attempts. Okay, part II. This time, at each attempt, I choose a key from all of my keys, and each of the keys is equally likely. What's our gut instinct of the best way to approach this probability question? What do we decide is pretty much always the best way to approach a probability question? We're just going to draw a tree. So what's the probability that I'm lucky on my first attempt? Well, I'm lucky on my first attempt if I just happen to pick the right key, which happens with probability 1 over k. Oh, nice. But k minus 1 times out of k, the door does not open. But now in this example, because I've got no memory, the next time I use a key, it opens with probability 1 over k, but it doesn't open with probability k minus 1 over k. Now, for the door to open on the kth attempt, sorry, the nth attempt, what two things need to happen for the door to open exactly on the nth attempt? How many times must the door not open? Yeah, so it needs to fail for all the previous attempts. So the door needs to not open for n minus 1 attempts, and then open. So we need And each of those failures happens with probability k minus 1, k over k minus 1 over k. And so we get n minus 1 failures. And then we get one success at the end, which is happens with probability 1 over k. Okay, now I, let's draw a tree. Attempt 1 is special because the door just opens with probability 1 over k. And then k minus 1 over k, it stays closed, it doesn't open. What's the probability that the door opens on the second attempt? And remember the strategy that the person is using. So I choose a key that I did not try the previous time. So at this stage, the person doesn't use the first key, and the first key was wrong. So he's choosing now only from k minus 1 keys on his key ring. Okay, but one of those k minus 1 keys will be the right key. So the probability of opening here is now one over k minus 1. And then the probability the door doesn't open is if he picks one of the remaining keys. So that's k minus 2 keys out of k minus 1 keys. Okay, so what is the probability? So what needs to happen now for the door to open on the nth attempt? So we need to have an initial failure, which is probability k minus 1 over k. Then we need to have n minus 2 failures like this. And then we have to have a success, and the success is with probability 1 minus k. Sorry, on the nth attempt is this. Okay, very quick question. And this is very marginal gains. But if I was to put this as my final answer on this step question, I reckon I would score 19 out of 20. What can anyone spot the problem with the answer that's suggested here? And this is just a little bit of a tiny little bit of professionalism in your work, really. Is there any value for n for which this does not work? Okay, yeah. There's only one special case where this fails, is opening at the first attempt, because opening at the first attempt is a special case, and opening at the first attempt is just 1/k. Okay, so as I say, this is just a little bit of professionalism. In the first part, I think you would have been docked marks if you didn't say that n had to live between 1 and k. And I think it's good practice to say that it's 0 otherwise. In the second attempt, in the second part, there's no special cases. In the third part, there is this special case of n equals 1, where you never reach the point where you're restricting for a key that you haven't used before. Okay, are people happy with that question? If so, put a thumbs up into the chat. Okay, just before I move on, do let me know if from the sort of COMPOS combinatorics sheet, if there's any question that you've looked at and that you would like me to go over, because of the questions I've prepared doing. I've got a feeling I might get through them before 7:30. So feel free to have a look at the COMPOS sheet and give me a suggestion. Okay, but this last one that we've done was just a careful tree diagram. Okay, now a slightly more combinatorics-y question. Actually, I've got an idea for what I might do as a little bit of a finale if you don't have any suggestions of COMPOS questions. Okay. Question number 14. So it says 3 pirates are sharing out the contents of a treasure chest containing n gold coins and 2 lead coins. It says the first pirate takes out coins one at a time until he takes out one of the lead coins. Okay, so we could go gold, 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 and then lead, and then he stops. And then the next pirate, she takes out coins until she hits lead, and then the remaining pirate gets everything that's left. And the question says, find the probability that the first pirate will have some gold coins. Then it says, find the probability that the second pirate will have some gold coins. And then part II, the probability that all 3 pirates will have some gold coins. Yeah, so by some, that just means greater than or equal to 1. That just, yeah, so it means not none. Okay. Again, this is from a STEP paper. And again, if it was a GCSE, it would tell you how easy or hard the question was. But I'm going to tell you that part I is easy. Okay, so by that I mean, if you think about it, you should just be able to put the answer to part I. You should be able to put the answer to part I into the chat. Okay, so yeah. So for the probability that the first pirate has some gold, gets some gold, it's just a complicated way of saying what's the probability that the first coin is gold. Okay, and that's obviously there's n gold coins out of n plus 2 gold coins. Part II is a little bit more is a little bit more subtle. Okay, so it says, what is the probability that the second pirate will have some gold coins? So any suggestion, and there's lots of different ways of doing this, but any suggestions? What needs to happen for the second pirate to have no gold coins? Have the first taken n-1 gold coins? Not necessarily, no. So the second pirate gets no gold coins precisely if the 2 lead coins are next to one another. Okay, so pirate 2 gets no gold coins if the 2 lead coins are next to one another. Okay. Any suggestions of doing of how to do the probability the other way around? So what's the probability that the 2 lead coins are? Oh, sorry, what if the first pirate gets all the gold coins? Well, if the first pirate gets all the gold coins, then it's still the case that the 2 lead coins would be together. They would just be at the end. So let's try and get the probability of that the 2 lead coins are together, and we'll do this. And then we'll just do 1 minus that to get the probability that the 2 lead coins are not together. So first of all, how many gold coins are there? There's n gold coins. Okay, and there's 2 lead coins, L1 and L2. How many permutations are there of the n plus 2 coins? So there's n plus 2 factorial permutations of the n coins, of the n plus 2 coins. If the 2 lead coins must be together, we can just regard them as a single coin. There's now, if we regard the 2 lead coins as a single coin, how many objects are there? Well, there's n gold coins, and then this one block of the 2 lead coins. Okay, so there are now n plus 1 objects. Okay, so the n gold coins and the double lead coin. With n plus 1 factorial orders. But why isn't the answer for the number of ways that the 2 lead coins can be together n plus 1 factorial? What other choice do we have? We could also have the orders of the lead coins. So the lead coins could go L1 then L2 or L2 then L1. So the orders, but we also have the lead coins could be in 2 orders. So therefore, there are 2 times n plus 1 factorial orders where the 2 lead coins are together. Therefore, the probability that the 2 lead coins are together is equal to 2 times n plus 1 factorial over n plus 2 factorial. Can anyone in the chat simplify 2 times n plus 1 factorial over n plus 2? Yeah, excellent. 2 over n plus 2. So the n plus 1 factorial cancels with the n plus 1 factorial in the n plus 2 factorial, but the n plus 2 factorial has an extra n plus 2. Okay, so the answer to part 2 is the second pirate gets gold. With probability 1 minus 2 over n plus 2, which is n over n plus 2. Can anyone come up with a simpler argument? And the simpler argument will really help doing part II. And sometimes the simpler argument only emerges when we've got the probability from some complicated argument. Okay. I'm going to suggest so what I'm going to look at now is a slotting argument. Okay, so let's imagine we've got the n gold coins. Okay, and what I'm also going to imagine, and let's imagine that we know, let's imagine we know that the first lead coin is between the ith and the ith plus 1 gold coin. So in other words, we've got gold, 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 and then the first lead coin is here. Okay, and we've got I gold coins here. Where could the second lead coin? Okay, maybe we've got the imagine we've got the two gold coins labeled with a 1 and a 2. So we've got the two lead coins labeled with an L1 and an L2. Where could the second lead coin slot in? So the second lead coin, which is L2, could slot in any of these gaps between so we've got any of these gaps between or outside the first n+1 coins. Okay. How many gaps are there for L2? How many spaces are there where the second lead coin could slot in? Well, there's n+1 coins, so there's a gap before each coin, but there's also another gap at the end, so there's n+2 gaps. And how many of these gaps are next to L1? Okay, so there are n+2 gaps, and 2 of these gaps are next to L1. So what's the probability that L2 is next to L1? Well, it's just the 2. It'll only be next to L1 if it slots into the 2 gaps that are next to L1 out of the n+2 gaps. So the probability is 2 over n+2. That's a little bit of a subtle argument. Can you just put your thumbs up if you understand that second argument, or put any questions into the chat if you don't? Oh, good, there's a thumbs up. Oh, so someone says, surely, what if L1 is at the start? Surely there'd be only one slot next to it. That's a very good question. But let's try that. Okay, if L1 is at the start, there's still 2 places L2 could slot in next to L1. It could either slot into the left of L1, so it would be here, or it could slot into the right of L1, which is here. Because notice we're only fixing the position of L1 relative to the gold coins. Okay, we're then asking, okay, where is L2 slotting into the rest of that list? So we can't say that we're not allowed to fix L1 as being at the start of the list of all the coins. Just as a quick show of hands, who likes this? Who prefers this permutations argument? So if you prefer permutations, write permutations. And who likes this slotting argument? If you prefer slotting, right slotting. Oh, we've got a vote for slotting. We've got 2 votes for slotting. We've got 3 votes for slotting. Everyone's voting slotting. We've just got 1 vote for permutations. Okay, there's lots of other ways. There's lots of other ways of doing this. Of doing this question. Okay, I'm just trying to think of other ways, but you could condition on the number of gold coins that the all 3 pirates have. Yeah, there's lots and lots of different ways, and this is a step problem. You can have a look at the model answers and so forth. Let's have a look now at III, which says that the probability, what is the probability that all 3 of the pirates will have some gold coins? Well, people seem to like slotting, so let's do III from a slotting argument. Okay, so let's imagine we've got all the gold coins. Okay, I'm just going to list the n gold coins here. For all 3 pirates to have gold coins, where must L1 where must L1 slot in? Or rather, where must L1 not slot in? Okay, we can't have L1 slotting in at the at either end, because if L1 slots in at the beginning, or if L1 slots in at the end, then either the first pirate or the last pirate doesn't get any gold. So all 3 pirates have gold coins if L1 does not slot in at the beginning or the end. Well, how many slots are there in total between the gold coins? Well, there's n gold coins and there's n plus 1 slots. Okay, so this happens with probability n plus 1 slots take away the 2 at the end over n plus 1. So we get n minus 1 over n plus 1. Okay, and if we do that, lead coin 1, L1, is somewhere in the middle. Where can L2 now not slot? So there's a few excluded. So the question is, for all 3 pirates to get gold, where can L2 slot? Or maybe it's an easier question to say, where can L2 not slot? Put it into the chat. In how many places can L2 not slot, and how many places are there? Yeah, so someone said it can't be at the beginning and it can't be next to L1. So how many forbidden slots are there for L2? 4. Excellent. The forbidden slots, it can't go here. Okay, at the left-hand end. It can't go here to the left of L1, because then pirate 2 would get no gold. It can't go here to the right of L1, because then pirate 2 would also not get any gold. And it can't go at the end, because then pirate 3 would not get any gold. Okay, but regardless of where L1 went, there's 4 forbidden places where it can slot. So there's 4 forbidden places. And that's 4 forbidden places out of how many places in total? Well, there's n plus 2 slots in total. We take away 4. So the probability that L2 isn't in forbidden slot is n plus 2 minus 4 over n plus 2, which is n minus 2 over n plus 2. And so what do we need to do to these probabilities to get the overall probability that every pirate gets some gold? We simply need to multiply them together. Okay, so we need that the first lead coin doesn't go at the beginning or end. Okay, so that it doesn't rot up the first or the last pirate. And then wherever that first gold coin L1 slotted, we need L2 not to slot in any of the 4 forbidden places. And so that's n minus 2 over n plus 2. So overall, the probability is n minus 1 times n minus 2 over n plus 1, n plus 2. Okay, now that's the right answer. Okay, that's not by any means the only approach. Okay, so there are lots of other ways of doing this question. I'll just get the source for you so you can have a look at the oh no, I'm not sure. But this question was is from a step paper. When I'll send to Vlad where it comes. I'll send to Vlad where it comes from. Okay, right. That is 7:30. Is everyone happy with that last example, or does anyone have any questions about that last example? Got happy. Okay, well, I will stop sharing my screen. I'll go back to the Zoom call. Right, well, that's the end of today's session. I hope you enjoyed it. Some nice probability questions. Any final comments before we go, or shall we say goodbye and reconvene after the summer? A few thank yous in the chat. Super. Well done. I hope you've enjoyed tonight's session. I will send out the PDF with the questions, and you can watch the videos again. You know, as I'm sure you know, this will be a summer of preparation for you, getting ready. I imagine most of you applying for either maths or physics. So you'll have admissions tests in the autumn, so either math or PAT, maybe a college admissions test if you're applying to Cambridge, and the summer holidays is the real time to do that. The COMPOS sheets are obviously a great resource. I'll check with Vlad if there's any way to contact us over the summer, but I'm certainly happy in principle if that can be arranged. If you've got any questions about COMPOS or questions that that you get from elsewhere. So, oh, there's a little question here. How much do PAT and STEP differ? I think that STEP is obviously aimed at maths and only maths. So the questions are mathematically very involved. There are also 20 markers. So the questions that you get in a STEP paper, will be long. Every single STEP question will be longer than any PAT question. PAT has got a mixture between short questions and long questions. So I think STEP is probably a notch of mathematical sophistication up. Obviously, PAT has got the mixture between maths and physics questions. Okay. Any other questions? Super. Well, have a lovely summer holiday. I'm sure there'll be some work here and there, but I also hope there's plenty of time to relax after a long academic year. So I will say goodbye and hopefully see you in September.